the balls can be identical or different, or and also the boxes are identical or different. Okay. So so two of the cases correspond to the permutations and combinations with repetition. And the third case is in which the balls are different, the boxes are the same, identical. We have the number of ways to distribute the balls into the boxes are calculated by what we call the Stirling numbers of the second kind, okay? Denoted by S and K. And you are given a closed form formula to calculate the Stirling numbers of the second kind corresponding to N balls and K boxes. Okay? And remember that for Stirling numbers of the second kind, we demand that the boxes are not empty. Okay? And if the if there are some empty boxes among the boxes, then we can simply calculate the sum of the Stirling numbers corresponding to N balls and J non-empty boxes with J going from 1 to K. Okay? So if some of the boxes can be empty, then we know that the number of non-empty boxes is something between 1 and K. And we have this formula. Okay, so we have this. Okay, and we have this this identity involving the Stirling numbers of the second kind, and you can use this if you want to calculate the Stirling numbers of the second kind. It will be easier to use this recurrence formula instead of this formula. Okay, because this formula of y, it looks pretty. It is not. It is kind of complicated to calculate. If you use a computer, you can see that it involves some factorials here and here, and there's a big exponent here. So maybe it will be easier if we calculate. If we use this formula to calculate. And if you, I don't know if you have seen the principle of dynamic programming in algorithms. So with this kind of recurrence formula, you can use dynamic programming to calculate the terms. Okay? And so for identical balls and identical boxes, we talked about integer partitions. Okay? So an integer partition of a number n is a way to write n as the sum of smaller positive integers. Okay? And here, in order to ensure that each way to write n as a sum of integers like this is unique, we can assume that we can arrange the terms in this sum in decreasing order, so that each way of writing is uniquely determined. Okay? And here we also demand that each term is strictly positive, okay? Because if we allow zeros, then there can be infinitely many ways to write. Okay? And so the number of ways to write a positive integer n as a sum, such a sum, is called the partition function Pn, P for partition. Okay? So this is a difficult function to calculate. We don't know the closed form formula, but there are approximation formulas in terms of power series, and which are surprisingly good. That means that the error is quite small. And so there are several versions. First approximations were found by Hardy and Ramanujan at the beginning of the 20th centuries, and There are improved versions of by Rademacher later. So I don't remember if I told you, but if you read or watch movies or documentaries about Ramanujan, then this is a very interesting person. Okay? So his story is a great inspiration for those who want to do mathematics, because he is someone from India who didn't have proper education, but he found results, and he writes the results that he found and sent to British mathematicians, Hardy, and then he was invited to England, to Oxford, to do maths. Okay? So there were some movies about him, and I think that a recent movie is The Man Who Knew Infinity, about him. And there are also documentaries available on the internet if you search. Okay, so that's all about the partition function. So we will not delve deeper into partition functions, because it is a very hard area of combinatorics. Okay? So it's just for general concept that we mention partitions and the names of these famous mathematicians here. Okay? So about today's lecture. So we have seen some identities, okay, involving binomial coefficients or involving Stirling numbers of the second kind. So in general, those identities are called recurrence relation. Okay? So a recurrent relation is a formula which establishes a relation between the terms of a sequence. Okay? So in many practical problems or theoretical problems, we want to estimate something, some kind of measure or quantity which depends on the input. For example, you have sometimes you have a problem or a program, an algorithm will take as input a string of certain length, and you want to estimate the complexity, the number of operations executed by that algorithm as a function of the input. Okay? And in many cases, the size of the input is an integer, and so we can express those quantities, those measures, as the terms of a sequence indexed by positive integers. Okay? And most of the time, it is difficult to calculate, to establish a formula or efficient computations of a general term of such a sequence. And a technique that we will look into in this lecture involves establishing recurrence relation, which allows us to calculate the terms of a sequence gradually, if we know some first terms of a sequence, and then we can use the recurrence relations to calculate the next term, and then the next term, and so on. Okay? And then in the second part, we will study a class of recurrence relation of which we know the solution. Okay? So, and then in the third part is a similar class. So, in fact, it is a class of linear recurrence relation, and we distinguish two cases of homogeneous and non-homogeneous. So now let us begin with some examples. In these examples, these famous examples, we will look at some problem, maybe well known or maybe not known to you, and we will see how we can establish relation. Okay. So first, in the first part, we try to look at some different examples of establishing recurrence relations between terms of a sequence, and then in the second part we will look into a particular class and we will look for the solution. But first we need to construct such relations before trying to solve them. Okay? So now, the classic example of recurrence relation is about Fibonacci sequence. Okay? So I guess maybe some of you have heard of Fibonacci sequence. It is a famous sequence, and you can see its occurrences in nature and in mathematics, in art, etc. Okay, so it is related to the golden ratio in art and in architecture. Okay, so this sequence, this problem can be stated as follows. Okay, so assume that you put a pair of rabbits on an island on which there were no rabbits at all. Okay, and we suppose that rabbits are animals which reproduce very fast. Okay, and we suppose that from 2 months old, they will be capable of giving birth to new rabbits. Okay, and here this is a fictional setting. Okay, we assume that the rabbits never die, and they reproduce regularly every month. Okay, so the question is that if we put an original pair of rabbits on an island and we let them be on the island without intervention, then what is the number of rabbits after n months, or n of integer? Okay. So now, as usual, we will look at some initial values. Okay. So here, for convenience, since the rabbits do not reproduce until 2 months, I create 3 columns here corresponding to the age of the rabbits. Okay, so the first column corresponds to the newborn rabbits. Okay, so those that are not, let's say, 0 months old. The middle column corresponds to the rabbits which are 1 month old. Okay, they are not newborn, but they are not ready to reproduce. And finally, the right column corresponds to the rabbits that are ready to reproduce. Okay, and we denote Fn, the number of pairs of rabbits on the island at month n. Okay, F for Fibonacci. So first we have only 1 pair of rabbits. So F1 is equal to 1. And after 1 month, this pair of rabbits becomes still 1 pair, but they are not newborn anymore. They are 1 month old. They are not ready to reproduce. So at the second month, we still have 1 pair of rabbits on the island. Okay? And now the next month. Now the next month for the next month, this pair of rabbits will become an adult pair of rabbits which is ready to reproduce. So they become an adult pair of rabbits, and they give birth to a new pair. Okay? So now we have F3, which is equal to 2. And so on. And now, next month, this this pair of rabbit, a newborn rabbit, become a 1 month old pair of rabbits. Okay, so this pair of rabbits stay the same, so they will move down here, but they give birth to another new pair of rabbits, so we have in total 3 pairs of rabbits. Okay? So pay close attention, because if you don't distinguish the 3 categories of rabbits and you try to calculate the number, you will quickly get confused. Okay? So it looks simple, but it is not trivial. Okay? So this is so if you don't have 3 categories, but you only distinguish the young rabbits and the adult rabbits, then it will be quite confusing. Okay, so but this way you can see that every month the newborn pairs here will move to the middle column. The pairs at the middle column move and merge with the pairs already in the right column, and then you clone the number the rabbits in the right column here. Okay, so here, so I repeat. For example, here in this month, after 1 month, this pair move over here. Okay, and then we make a copy of this pair here. Okay, so for the next month, this pair move here. There's nothing here, so you have no new adult pair of rabbit here, but you still make a copy of what is here to here. Okay, so as you can guess, the following month, the 5th month, you will have 2 adult pairs of rabbits. Okay, so this one here move here, so now we have 2 pairs in this category. We have 1 pair here, which was the newborn pair the previous month, and then we make a copy of this. Okay, so these 2 pairs will give birth to 2 new pairs here, and we have 5 pairs of rabbits in total. And then you can continue, and you find F6 is equal to 8. And until now, if you look at the numbers here, you can see a pattern, or maybe you know already that. You can see that 2 here is equal to 1 plus 1. Okay? 3 is equal to 2 plus 1. 5 is equal to 3 plus 2. And 8 is equal to 5 plus 3. And you can guess that if you continue on, you will find F7 is equal to 13, which is 5 plus 8 here. Okay? So, but that is an observation, and how can we prove it? How can we be sure that it is correct for any index n, for any month? Okay? So maybe it is true for the first few months, but what if from a certain moment it stops to be true? So now we will show that we will use the observation that we talked about just now. So we look at the 3 columns, and we look at the movement of the pairs of rabbits in the column. Okay, so let's see, for example, this month and this month. Okay, so and we compare the number of pairs of rabbits between 2 consecutive months. Here, we know that the rabbits. So here we assume that the rabbits do not die. So all the rabbits which are present in the previous month we carry over to the next month. But we will have some newborn rabbits here. So here you can see that the same color corresponds to the same rabbits. Okay. So here we have a different color, but we have a connection here because the number of rabbits here is the same as the number of rabbits here, because of the hypothesis that the adult rabbits, each pair of adult rabbits, give birth to a new pair of young rabbits. Okay? So here we have blue becomes blue, red becomes red, and red will give birth to blue, and they have the same number here. Okay. So now we need to compare. So f of 6 here, you can see that it is equal to f5 plus these newborn rabbits, and we must show that these the number of newborn rabbits here is equal to f4 here. Why? So in fact, if we go back 2 months, then the adult rabbits here present at month 6 are exactly all the rabbits which were present at month 4. Okay? So here at month 6, if they are at least 2 months old, that means that they must exist already at month 4. Okay? So that means that the number of adult rabbits here is equal to the number of rabbits, total rabbits, 2 months prior. Okay? So that means that the number of newborn rabbits at this month is equal to the number of the total number of rabbits 2 months before. Okay? So you have here blue becomes blue, red becomes red, and green. Green doesn't become green, but green here have the same number of pairs of rabbits. Okay? So that means that the total number of rabbits here in this month is equal to the number of rabbits of the previous month plus the number of rabbits of the month before. Okay, so in summary, so I write down the key observation here, and from this key observation, you will see that, and combined in combination with this picture, you can see that we have the difference here. The difference here, which is the number of newborn pair, and if we write it as a formula, it will be equal to fn minus fn minus 1. And this statement, this observation, if we use notation, then this is the same, the equivalence of this observation, but in formula, in symbol. Okay, so we have the number of newborn is equal to the number of rabbits 2 months earlier. And if you change if you change this term to the right, then you get this relation. F of n is equal to fn minus 1 plus fn minus 2. And this relation, since our sequence starts with the index 1, so that means that n for n minus 2 to be at least 1, we must have n greater than or equal to 3. So this relation applies to all the terms of our Fibonacci sequence starting from n equal 3. Okay? So this is called our recurrent relation, which but here, note that a recurrence relation alone doesn't define our sequence. Okay? Because if you change the initial number, you can see that here, from here you know that f3 is equal to f1 plus f2. Okay? So if you change the initial values, then you will have a different sequence. Okay? So in order to define a unique sequence, you need, in addition with a recurrence relation, what you call the initial conditions. Okay? So now we will take this recurrence relation and these initial conditions. Okay? So here you need two terms. You need to go back 2 steps in order to calculate the next term. So it makes sense that you must know two initial values in order to determine the whole sequence. Okay? So you can see, we will see later in the general linear reconciliation. Okay? So this is called the Fibonacci sequence, and in a later part we will find a closed form formula for the term of the Fibonacci sequence. Yeah, if you study algorithm, then you will see that you can do an exercise you can try to write a program or an algorithm to calculate the general term of the Fibonacci sequence. Okay, and try to see if you can do it rapidly or. So here, if you do this, then it will be quite costly for the naive way, but there are fast way, clever ways to calculate this sequence very, very rapidly. Okay, so if you change the initial conditions, then you will have another sequence. So the Fibonacci, whenever you talk about the Fibonacci sequence, it involves two things. Okay, first you need this famous reconciliation, but you also need the initial conditions. Okay, so the relation alone doesn't define the Fibonacci sequence. You need this, and it depends on the textbook or document. Sometimes sometimes this sequence is defined, you give the first two terms are 0 and 1 instead of 1, 1. Okay? So there may be some differences in the way you choose the first values. So it may start with 1, 0, 1, or it may start with 1, 1. Okay? But basically the other terms of the set. Okay, so do you understand this construction, the part here when we explain the relation? So if you haven't grasped this explanation, you can a practical way is to try to redo it yourself, okay? To redraw the picture and to see it, to understand. Okay, so the next example is also a famous example in computer science, in algorithm. Okay, so you may have heard of the problem of the tower panel. I don't know why it is called the tower panel, and no one knows. Okay, no one knows. There are some speculation, but the definite reason is still a mystery, and maybe no one will ever know why and who named it the tower panel. Okay, so here is the rule. So you have three, let's say, wooden peg. Okay. And you have some circular discs of different sizes. And in the initial configuration, the discs are put on top of each other, and they have a hole in the middle so that they can be put on those pegs. Okay? And the rule is that any disc must be put above a larger disc. Okay, so you cannot put a large disc on a smaller one. And now the challenge is that starting from this initial configuration, you need to move all the discs to another peg. Okay? and always respecting these rules. And each time you can only move one disc. Okay, you cannot move two discs at a time. So that means that at any moment you can only remove the topmost disc from a pile. Okay, so the question is that what is the smallest number of moves you need to do? Okay. So the challenge is to move n discs from the first peg to the third peg without violating these constraints. Okay? So one disc at a time, and each disc must not be put on top of a larger disc. Okay? So now, for example, if you have only one disc, then it's easy, right? You only move one move and you're done. So if you have two discs, so it's a little more complicated. So if you need to move this pile to the third peg here, first you need to move the smaller disc here to the middle peg in order to so that you liberate. Let's say you liberate this larger disc. Okay. Because if this larger disc is blocked on top of it, then it cannot move. And now it is free, so you can move it here, and then only at this point you can move the smaller disc on top of it. And so so you need 1, 2, and 3 moves for 2 discs. Okay. So now you can try with 3 discs, but now I will illustrate how to do it in the general case. Okay. So you observe that. So here, suppose that here is a pile of n discs. Okay. So I didn't draw all the discs here. So we are interested in, what we are interested in is the bottom one, the largest disc, and all the pile above it. Okay? So now you know that if you need to move this pile of disc to this peg, then first you need to, so you know that when you're done, this bottom disc must be also the bottom one here. So in order to move the bottom disc here to here, you need to remove all the discs above it. Okay? And the second condition is that if you want to move this bottom disc here, okay, sorry, so this peg must be free. There must be nothing. That means that everything here on top of it, the only choice is that everything here must be here. So we have this configuration. Okay. So in order to liberate both this disc and the third peg, we need somehow to go from this configuration to this configuration. And if you move all the discs here to the second peg, then the only possible configuration is this one, because you cannot put a disc on top of a smaller disc. So when you move all the n-1 discs here to here, they must still be arranged in the order from larger at the bottom to the smaller at the top. Okay? So now, how many moves do we need in order to go from this initial configuration to this configuration? So it is, if you ignore the blue disc here, so it is as if you move the whole n-1 pile here to here. Okay? So it is the problem, but with one fewer disk. So in order to go from here to here, you need exactly Hn-1 steps. Here H of n denote the optimal number of moves for n disk. Okay. And now, once we have this configuration, we move this blue disk here. And we need only one move to do that. And now finally, we need to put this green pile on top of the blue disk here. And once again, it's similar to the first phase here. We need another Hn-1 steps. Okay? So from here to here, assuming that each time we do the optimal way, there is no unnecessary step. Okay? We do in the fewest number of moves possible. Then from here to here we need Hn-1, which was the optimal number for n-1 disk, and then we need 1 to go from here to here, and then another Hn-1 from here to here. Okay? So if we take the sum, we conclude that Hn is equal to 2 times Hn-1 plus 1. Okay? So you can verify with the smaller examples here. So here you can see that for H1 equal 1, H1 is equal to 1, H2, so 2 times 1 plus 1, you get 2. And if you continue with 3 disks, you will find that H3 is equal to 7. Okay, so to summarize, for the optimal number to move n disks, you have this recurrence relation, which applies for n going from 1 to infinity. Okay? So here Hn is equal to 2 times Hn-1 plus 1, and the initial condition is H1 equal to 1. Okay? So here, in this recurrence relation, you need only one term on the right hand side. So that means that you need to have only one value for in the initial condition. Okay? So you can continue this calculation and you can get 1, 3, 7, 15, and you may see something quite familiar here. If you add 1 to each value, then you have 2, 4, 8, 16, and then 32, and so on. And you can prove by induction that the general formula for the terms of this sequence is Hn is equal to 2 to the power n minus 1. Okay? So is it a large number or a small number? So you can see that here, if you put another disk, then the number of moves increase in an exponential way. Okay? So it almost double, or maybe more than double each time. Okay? So there was a legend that in a temple in the mountains far away, there were 64 golden discs arranged on 3 pegs like this one. And the monks who live in that temple will try to move the disc from the initial peg to another peg, and when they are done, it will be the end of the world. And now that you have the formula, you can ask then, if that legend is true, then when will be the end of the world? Or in other words, how much time do we have left? Okay? So in the legend, n is equal to 64. So if you put it in some in the computer and try and tell it to calculate the value for you, then it would be approximately 18 billion. Okay? So you need this many moves for the pi of 64 disks in the legend. Okay? So what does it mean? Can you have an estimation how much time is it? So if you suppose that the monks work continuously without break and they move very fast, very skillfully, they only need 1 second for each move. If you divide this by, if you do 1 move per second, then this is roughly equivalent to almost 603 billion years. Okay, and you know that this far exceeds the age of the universe, so you don't have to worry about that old story about the monks and the end of the world. So in any way, the universe will be terminated long before the monks finish their work. Okay. The next example is about a code. Okay, so in the language of computer, a code is simply a set of words. Okay, you use for a certain purpose. So suppose that you use a set of code words which involve, in order to check if a code word is valid, you only count the number of zeros in the code word. Okay, so this is similar to the notion of checksum. You see that whenever you download some important files, if you want to check the integrity, you will run some function on the file to calculate some value, and you compare that value with the provided value to see if there is any damage, any corruption to what you downloaded. Okay, so but this is a very naive, very simple version of checksum. Okay, so let's say that here the checksum function is simply the number of zeros in your code word and modulo 2. Okay, so if you have an even number of zeros, then the code word is valid. And if you have an odd number of zeros, then the code word is not valid. For example, here you have an example of a valid code word in which there are 2 zeros, and an invalid code word in which there are 3 zeros. Okay. So now the question is that how many code words of given length are there? That means that if you denote the number of code words, the valid code words of length an, then what is an? Can we find at least a recurrence relation for an? Okay. So now before we look into the relation, let's try to calculate some initial values, because we need initial conditions anyway. Okay? So for n equal to 1, it is easy, okay? You have only the word length is 1, and if the code word is valid, then it can only contain 0, 0 zeros. Okay? Because you know you want that the number of zeros is even, and here you have a max. You have only 1 character, so you have no zeros at all. And so the valid code words of length 1 are these code words, and you have a1 equal to 9. Okay? So what about a2? For a2, 4 code words of length 2. If they are valid, then they can contain either 0 or 2 zeros, okay? Because you need an even number of zeros. So if you have 2 zeros, then the only code word that satisfies is 0, 0. Okay? And if you don't have any zero, then what does it mean? If you don't have any zero, you have a code word of length 2. That means that you have 2 characters to fill. Okay? So if you don't have zeros, that means that the first character can be any digit from 1 to 9. Okay? And the second character, the same applies. Can be any digit from 1 to 9. Okay? So you have 9 choices for the first character and 9 choices for the second character. And here we have the product rule. And so we have 9 by 9, which gives us 81 words. Okay? And now we combine the 2 cases. So 1 plus 81, and we have 82 equal to 82. Okay? So, but if you look at the 2 values here, there is no trivial connection. Okay? There's no trivial connection between these 2 values. So how can you get to 82 starting from 9? Maybe it's 9 times 1 plus 1, or I don't know. So here is a technique to establish reconciliation. Okay? So in order to establish a reconciliation, you can either explore the okay. So we used a similar way in the Tower of Hanok, and now we will do the same. That means that instead of constructing a code word of length n, we will try to see how you can create a code word of length n from a word of length n minus 1. Okay? And now you try to reduce the size of your object to a smaller object, so that you will express the small object in the previous term of the sequence. Okay. So now, so now maybe you will see it more clearly in this example. So now we want to establish a reconciliation between the number of code words of length n and the number of code words of smaller length. Okay? So now suppose that n is at least 2. We will look at the first or the last, if you like, or whichever you like, character of the word W here. Okay? So now let's see the first character of the word W. Then the word W is the concatenation of the character C and another word W prime of length n minus 1. Okay? If you cut the first character, and we will distinguish 2 cases based on the fact that whether this first character C is 0 or not. Okay? So in the first case, suppose that this character C is not a 0. We know that the condition for W is that it contains an even number of zeros. So if C is not 0, that means that the number of zeros in the word W prime is also even. Okay? So in other words, W prime is a valid code word of length n-1. Okay? So now, in order to construct a code word of this type, we can first choose a letter C. Now you have C and then W prime here. Okay? So C, you have the values from 1 to 9 because it is not 0. You have 9 choices. And we have seen that W prime is also a code word of length n-1. So that means that you have a n-1 choices for W prime. And now you apply the product rule and get 9 times a n-1 code words of this type. Okay? So of course you can guess that the case number 2 is the case in which this C here is 0. That means that we have this type of code word. Okay? So now, that means that in case number 2 we need 0 followed by a non-code word of length n-1. But how can we express the number of non-code words in terms of the number of code words? So you know that if you count the total number of words of length n-1, we have 10 digits. So we have 10 digits and we have n-1 characters. So that means that we have in total 10 to the power n-1 words of length n-1. Okay? And now among these words there are a n-1 words which are valid. So the number of words which are not valid, this number we want to compute must be the complement of this. Okay? So you take the total number of words of length n-1, you subtract the number of valid code words, and what you get here is the number of invalid code word. Okay? So now, for this case, the number of word W which fall into this case is 10 to the power n-1 minus a n-1. And now you sum up the two cases and you get what? You get an is equal to 8 times a n-1 plus this exponential of 10 to the power n-1 for n equal to 2 onwards. Okay? And our initial condition, of course, we need an initial condition in order to determine our sequence. So the initial condition here is easily calculated by listing all the code words of length 1. So you have A1 equal to 9. So this is the recurrence relation for the number of code words of length n. Okay? So that is how you establish. So you can practice this in the tutorial class. Okay? So the takeaway here is that you try to reduce the size of your object so that you can express it in terms of the smaller objects. So here you have a word of length n. You try to cut the character to bring it, to reduce it to words of length n-1. And when you have n-1, you can express in terms of the previous terms in the sequence. Okay? So we have seen 3 examples. Okay? So incidentally, in the these three examples have a common point. Is that you can see that here fn is equal to fn minus 1 plus fn minus 2. It's a simple sum, okay? You can see, or if you are maybe in terms of algebra, you can say that fn is a linear combination of the previous terms. Okay, so it is linear because the degree here is only 1. So here the same. You have this relation is also a linear relation because you have the thing on the right hand side is a linear function. And here, this relation is also a linear relation, okay? But the difference is that for the Fibonacci sequence, you only the terms of the sequence are involved. So the linear relation in the Fibonacci sequence is called a homogeneous linear recurrence relation. Homogeneous, đồng nhất, okay? That means that there are only terms of the sequence. There are no constant, no other term. And the two latter cases are called non-homogeneous linear recurrence relation. Sorry, not đồng nhất, thuần nhất, okay? Thuần nhất, không thuần nhất. Có nghĩa truy hồi tuyến tính. Okay, so here it is not homogeneous because you have this term here, which is not a something, but it is still a function of n-1, but it is not the term of the sequence. Whenever on the right hand side you have only the terms of the sequence, then the relation is called homogeneous. And whenever you have other terms, whether it is a constant like this one over here. So this relation is non-homogeneous because you have a constant here. And also, so you may have not a constant but even a function of n here. So the formula, the relation for the tower handle is not homogeneous. This one is not homogeneous either. And the first one about Fibonacci sequence is homogeneous. Okay. And so in the second part we will state the general solution for homogeneous and non-homogeneous linear recurrence relation. And now we take a break. Okay. Okay, so now to the more technical steps. Okay. We have seen the examples, and now we give a formal, more abstract, general definition of a homogeneous linear recurrence relation. Okay? So, as you have seen, we say that a sequence AN satisfies a recurrence linear relation if the term AN can be expressed, can be calculated in terms as a linear combination of the previous term here. So, so in the case of Fibonacci sequence, we have k is equal to 2. Okay? So here, this is a linear combination. Okay? So you have a n minus 1, n minus 2, etc. And c1 here, c2, and ck are constant, are coefficient parameters. Okay? So here, an important remark, we must insist that here the coefficients can be zeros, but except for the last one. Okay. So here ck is non-zero. That means that in order to calculate an, we need to go back k terms. Okay. So some of the if a term is not present in the relation, then it simply means that the coefficient is 0. Okay? But we need the last one. We need the last coefficient to be non-zero, so that this relation is determined uniquely. Because if you allow the last coefficient as 0, then you can extend, you can add other terms, so which doesn't improve anything. Okay? So here, if the last non-zero coefficient corresponds to the term n minus k, then we say that the recurrence relation is a degree k. Okay? So the degree of a recurrence relation is the number of terms we need to go back. Okay? So, for example, for example, for our Fibonacci sequence, we have f n equal to f n minus 1 plus f n minus 2. So in this case, the degree is 2. Because we need to go back 2 terms, okay? And the coefficients are C1 is 1 and C2 is also 1. Okay, so of course, this is a recurrence relation, and if we need to solve for the sequence, if we want the sequence to be well defined, then we need to add the initial conditions. Okay? So in general, for a recurrence relation of degree k, how many terms you need to know in order to define the sequence? Okay, so here you see that you need to know the first k terms of the sequence. If you know the first k terms, then you will know the term k plus 1 and then k plus 2 and so on. Okay? So for a relation of degree k, you need, the initial conditions contain k terms. Okay? Okay, so among the examples that we have seen, the first one about Fibonacci sequence is homogeneous linear recurrence relation of degree 2, and the 2 others are linear recurrence relation but not homogeneous. Okay? And in order to solve, so here I will present to you the general result, and then after that we will apply the result to concrete examples. Okay, we will see how we use the result to solve the Fibonacci sequence. Okay, so in order to solve a linear relation, we introduce what we call the characteristic equation. So it is a polynomial equation of this form. So the coefficient of the equation is, so in order to find this equation, you simply take this, okay? You take the relation. So here you will replace an with x to the power k, and each time and an minus 1 with x to the power k minus 1, and so on, okay? So when you go back until an minus k will correspond to x to the power 0, which is 1. And then you change the sign, you put everything on the left hand side, and you get this one, okay? So this corresponds to an. You can see an minus 1, and so on. So this is a1 and a0, n minus k plus 1 and n minus k. Okay. So this equation is called the characteristic equation. So as you know, the polynomial equations are not easy to solve, and in general, we know that for equations from degree 5 upwards, there is no closed form formula. Okay, so in practice, in the exercises, you will only need to work with quadratic equations, and in some cases cubic equation, but with roots that you can easily find. Okay. Okay. So the idea is to solve this characteristic equation, and we call the roots of this equation the characteristic roots of the corresponding relation. Okay. And now the general solution. So here we only talk about the relation. Okay, there is no initial conditions yet. We only care about the recurrence relation. And suppose that we somehow can solve this equation, and we can get all the roots of this equation, and we get a set of characteristic roots of the relation. So for example, if we look at the Fibonacci sequence, then the corresponding characteristic equation corresponding to this is what? So we have degree 2, okay? So the term corresponding to Fn here will be x squared, okay? And then we will add the terms with decreasing power. So here is x and x to the power 0, okay? So if you change you put everything on the left hand side, then you get this equation, okay? So this equation is, you know how to solve a quadratic equation, okay? So the roots of, so you can, what is the delta of this equation is 5, okay? So the solution is 1 plus or minus square root of 5 divided by 2, okay? So in this case, for the Fibonacci sequence, we have two different characteristic roots. Okay. So the general form, the form of the general solution to a recurrence relation will depend on whether the roots of the characteristic equation are single roots or multiple roots. tức là ghép đơn hay là nhân bội. Okay. So the case that we use the most is relations of degree 2. Okay, that means that k equal to 2, because you know how to solve the quadratic equations like this one. Okay, so we will talk about this case in particular because it is a case that you use the most. Okay, so you know that for a quadratic equation you have two cases. Okay, so if you use complex number, then you know that a quadratic equation always have two roots. Okay, either two different roots or a double root. Okay. So now, for the first case, suppose that this everything goes well and our characteristic equation has two different roots, namely R1 and R2. Okay. Then we will try to the general solution to this relation will have the form alpha times R1 to the power n plus beta times R2 to the power n, where alpha and beta are two coefficients to be determined according to the alpha and beta may be calculated based on the initial conditions. Okay. So here, in other words, if you take our R2 here, so that means that the base solution of such an equation is in the form R1 to the power n. So it is a geometric sequence, okay, of so this is a geometric sequence, and this is another geometric sequence. So you can think of this as I don't know what you have seen in linear algebra, so you can think of this as a linear combination of two solutions, two basic solutions. Okay, so one basic solution is this geometric sequence, and another solution is also a geometric sequence. And if you combine those two solutions linearly with some constant here, then you get a general solution for this relation. Okay. So this is the general form. But if you have a particular sequence, that means that you add the initial conditions, then you will replace n here with 0 and 1, or 1 and 2 if your sequence starts with 1. Okay? And then you plug them in order to calculate your concrete values of alpha and beta. Okay? So that is the principle. So let us use this to solve our Fibonacci sequence. So here we already know that for our Fibonacci sequence we have two distinct roots, characteristic roots, which are this. So you can see that one of these, the number 1 plus square root of 5 divided by 2, it is what is called the golden ratio in art and architecture. Okay? So that's why there's a tight connection between Fibonacci numbers and the things you measure. So you have R1 and 2 are 1 plus or minus square root of 5 divided by 2. Okay? And you have the initial, so the general solution is, you know that n is equal to alpha 1 plus square root of 5 divided by 2 to the power n plus beta 1 minus square root of 5 divided by 2 to the power n. Okay? So now it remains to calculate alpha and beta. And we will use the fact that, so I don't know if here we use f0 or f1. Okay, so in the example of the previous part, we start the sequence with f1, but now we can start with 0. Okay. So you know, if you replace n here with 0, then f0, according to this formula, it will be equal to alpha plus beta. Okay, because any number to the power 0 is equal to 1. And f1 will be equal to 1 plus square root of 5 divided by 2 alpha plus 1 minus square root of 5 divided by 2 beta. Okay? But because of the initial condition, we know that this is equal to 0 and this is equal to 1. So you have a system of two linear equations and two unknowns in alpha and beta. And you can easily solve these two and find that alpha should be 1 over square root of 5, beta is minus 1 over square root of 5. So here you can verify alpha and beta are opposite of each other. Their sum is 0. Okay? And they also satisfy this equation. And now the final step is to plug everything into that formula. And you get alpha, you replace alpha with 1 over square root of 5 and beta with minus 1 over square root of 5. And you get this. This is the general formula for the Fibonacci numbers. So it looks weird, right? Because how? Because you know that Fibonacci numbers are integers. But here, this doesn't look integer at all. But if you expand all these expressions using the Newton binomial formula, then you can see that there are the terms which contain square root of 5 will cancel each other out, and you can see that the rest will be a sum of integers. So that will resolve our doubt that it doesn't look integer. But in fact, if you simplify, then it is an integer. Okay? So it is a curious result. So this is how you solve a reconciliation. So I repeat the steps. First, you establish the characteristic equation, okay? And then you solve this characteristic equation. So for the case where you have two different roots, like this one, so it is the easy one. You write the general formula in this form, where these coefficients are to be determined. And in order to determine these coefficients, you use the initial conditions, okay? So you replace n with 0, 1, 2, 3, etc. So here we have degree 2, so you will replace n with 0 and 1, or with 1 and 2, depending on whether your sequence starts with the index start at 0 or 1. And then you get a system of two linear equations and two unknowns. You know how to solve this, right? In linear algebra. Or even if you don't know linear algebra, you can solve it using elementary algebra. Okay, so if everything everything goes well, you find your values of alpha and beta, and you plug in. You find these formulas. Okay? So once again, these formulas may be useful. They look pretty, and they may be useful to derive other properties. But if you are only interested about calculating the sequence, then maybe it is more efficient to use recurrence relation. Okay, so it's easier to program and to calculate. But if you want to look further, deeper into the properties of the sequence, then you may have to use the formulas like this one. Okay, so what about the case where you have only one root? So in other words, you have two roots are equal to each other. So in this case, we have a similar form, but now you can see we don't have a linear combination of two geometric sequences, but you have only one geometric sequence R0 here. So this you can admit this formula, and then the other steps are the same. Once you have this formula, you also have two coefficients to be determined, alpha and beta here, and you use the initial conditions to establish a system of two linear equations. You solve for alpha and beta. Okay? So now, let's try this relation. So you have this recurrence relation, so you can see that the characteristic equation here is equivalent to x minus 3 squared equal to 0. Okay, so the left hand side here is a square. So the only root is 3. And according to the result above, the general formula for an, we will have this form for the general term. Okay? And now it remains to calculate the coefficient alpha and beta. So now you can try to write out. So for n equal to 0, what do we have? For n equal to 0, the second term, because there is a factor n here, 0. So in this case, it's actually simpler. So if n is 0, then the term corresponding to beta will disappear, and you have a0 is equal to alpha, and then a1 is equal to 3 alpha plus 3 beta. Okay? So if our condition is a0 is 1, that means alpha is equal to 1. A1 is equal to 6. That means that. So if we replace alpha with 1 here, we will have 3 beta equal to 3, and beta is also 1. Okay? So in other words, the general term for this sequence is this one. Okay? So, for the case of degree 2, everything is easy. Okay? You only have to remember to distinguish two different cases, whether the roots are different or not. And if the roots are different, then you know that you have this nice form. You know that you have a linear combination of the two geometric series. And if you have unique roots, it's a little more complicated, but not too much. You can write down this whenever you are not sure. You can always consult your documents. Okay, so for the sake of completeness, we introduce the general solution for the general case. So we repeat this. So also the easy case is, or more simple case, is when all the characteristic roots are distinct, are pairwise distinct. So in this case, similar to the case of degree 2, the general solution will be a linear combination of geometric sequences like this one. Okay, so this is where all the roots are pairwise different from each other. Okay, so once again, if you have this form, you will use the initial conditions to calculate the values of the coefficients alpha 1 to alpha k. Okay, and you know the general technique to solve a k by k system, linear system. And this one looks more complicated, but you can always look at this. You don't need to know this by heart. Okay? So if, in general, if you have roots with multiplicities m1 to mt, okay? So in the case of double root in degree 2, that means that n is equal to 2. But now suppose that in the general case, you may have not only one, but many different multiple roots, and we suppose that the multiplicities of all the roots are these values. That means that each mi is a positive integer, and then the sum is equal to the degree of the equation. Okay, so then the solution, we take this form where each, so here P1n is a polynomial in n of degree at most m1 minus 1. So I will go back to the case, to this case. Okay, so here if you put R0 as a common factor, then so in this case the multiplicity is 2, alright? And our formula is an is equal to, we put r to the power n here, and inside we have alpha plus beta n. Okay? So this is the polynomial in n of degree 1, degree smaller than 2. Okay? And so similarly, in the general case, you will have a sum like this one. Here, R1, R2, R3 are different values. Okay? So here, HP here is a polynomial in n. So remember, it is a polynomial in n, but not in R. And the degree of each polynomial is smaller than or equal to the corresponding multiplicity minus 1. So in this example, we have the multiplicity is 2, so the degree is 1 or 0. Okay, so here if beta is 0, then the degree is 0. Okay, so this is a general example, and you may do 1 or 2 exercises in this one, but not too many exercises, because whenever things are complicated, we will try to solve by numerical methods. Okay, so what about the non-homogeneous case? So if in the homogeneous case, you can see that it works because you can verify if you have a solution of this form with two coefficients alpha 1 and beta 1. So let's see why it works. In fact, if you have Am is equal to alpha R1 M plus beta R2 M is a solution, that means that you verify the relation. You calculate Am minus C1 A n minus 1 minus C2 A n minus 2. Okay? So if we use this formula, then this will become, if we group all the terms corresponding to R1 together and all the terms corresponding to R2 together, then you have alpha R1 to the power n minus C1 R1 n minus 1 minus C2 R1 n minus 2. And similarly for beta, you have the same, but with R2. Okay? So this, if you put the common factor here outside, you will get alpha R1 n to the power 2, and inside you have R1 squared minus C1 R1 minus C2, and the same for R2. Okay? So you can see that this is zero because R1 is a solution to this is a characteristic polynomial. Okay? So this is 0 because R1 is the root. So that means that if we have this form, how we find this form is a different story, but it is easier to verify. If you plug this into the relation, then you can see that it satisfies the relation. Okay? And why? How you get the result, and why there are no different results, no other solution is another story. But for our purpose, we admit that these are all the solutions for this relation. Okay? Now you can see you cannot do the same for non-homogeneous relation. That means that you have if you have a trailing constant or a term, another term here. If in your relation you have another term which are not this, for example, you have a constant C, then it will not hold true anymore. Because in that you can verify maybe is leave alone to explain it on the table. You can write, you cannot repeat this argument, this calculation, if you have a term, a non-homogeneous term in the relation. Okay? So that non-homogeneous term can be anything. But here we consider the case where the non-homogeneous term is a function in n. Okay? So it may be a constant. A constant is also a function, or a polynomial, or anything. Okay? But it is not zero. So here you have a part which resembles non-homogeneous relation, but you have another term. So the addition of this is, you can think of in a similar situation in physics, when you have oscillations, you may have, if it is homogeneous and a closed system, then maybe it's easier to find a beautiful solution, but whenever you have noises, then it will be complicated. You will not have the nice solutions anymore. Okay, so but for now, for this kind of relation, so you can see that for the tower panel and for the case of code words, we find ourselves in this situation. The idea here is that if somehow you know a particular solution to this non-homogeneous relation, then you take this solution and an arbitrary solution to the corresponding homogeneous relation. You always have some you always associate this. If you remove this, then you obtain a homogeneous relation, okay? So the idea is that if you have a particular solution and you combine it with a solution of the corresponding homogeneous one, then you also have a solution to the non-homogeneous relation here. Okay? And we admit the result that those solutions are all the solutions to this kind of relation. Okay? So now it becomes less complicated. So instead of trying to find all the solutions in a general way, we only need to find a particular solution to this relation. Then we solve the corresponding homogeneous relation, and you add the particular solution. You have all the solutions of this one. Okay? We have 5 minutes, so you can try this with the problem with tower panel and the problem of code word, and in the exercises too. So, for example, consider this relation. You have a relation of degree 1. Okay? Whenever you have a relation of degree 1, so the solution is simple. You know that it is a geometric sequence. But now we have a trailing term here, which a non-homogeneous term here. Okay? So this homogeneous relation is easy. If you use induction, then you know that the general solution is alpha times 3 to the power n. Okay? Where alpha can be any constant. Okay? So here we leave the coefficients, the general coefficient alpha here. We haven't determined alpha yet. So now we try to look for. You can verify that. So now, in this example, I give you a particular solution, and later we will see there is a formula to find a particular solution. So here we admit that this one is a particular solution to this equation. You can plug it in, and you can see that it verifies this equation. So that means that the general solution for this relation would be this particular solution here, plus the general solution to the homogeneous relation here. And we get this form. Okay? So now we have this form, and it remains to calculate alpha using the initial condition here. And finally we get, if we replace n with 1 here, so we have minus 1 minus 3 halves plus 3 alpha is equal to 3. And you can solve to find alpha is equal to 11 divided by 6. And the solution will be this one. Okay? So how do we find this? I will give you this result. You don't need to prove as the previous result. We admit this one, and you will see how to use it in the exercises. Okay? So here I state this general result and the use of it. You can use case by case. Of course, in the exercises you will work with small and simple numbers. So the calculation can be done by hand. It's not complicated. Okay. And in the exam and in the test, you can always look at the documents. Okay. So you do not need to know this by heart. But you need to grasp the general idea. Okay, you must understand and remember the ideas, but not the detailed formula. The detailed formula can be consulted in the document, but if you don't see the idea, you don't know what the formulas talk about, what's the meaning of the formula, then it will be difficult. Okay. So here, as usual, we distinguish two cases. When S is not a root of the characteristic equation. So here there is a remark that if there is not this term here, that means that S equal to 1. When you do the exercises, you should take pay attention to it. Okay, so that if there is no term here, that means that S is 1. And you verify if S is a root of the characteristic equation or not, and depending on the outcome, you apply either of the two cases. Okay, so next time we will use this result to find a formula, a well-known formula for this. Okay, you know this how to calculate this sum, but we will see how we arrive at the result if we look at this as a recurrent expression. Okay? So the slides are available on Moodle as well as the list of the exercises. Okay, so next week we take another break, and when we go back, I think that you will have a test or something to do your class. Okay, so be sure to get yourself well prepared for the test. Okay. Are there any questions? If not, then thank you for your attention and see you in 2 weeks.